All right, so this is number 53 on the homework from yesterday. So it would be page 343. It's a compound interest problem. And it's doing a couple of things that we did not do with the compound interest yesterday. It gives you all the information that we talked about. Part A simply wants you to write an equation that represents the situation. And so that's where you'll use that formula that we did yesterday. So it says that we're going to invest $82,000 at 4.5% interest. So 4.5, when I move it to a decimal, would be 0.045. Quarterly is 4 times a year. And then this is one thing we did not do yesterday is it doesn't give me how much time. So if it doesn't give me how much time, then that's our X value essentially. But here we're going to call it T because it's time. And what we'll do here, so that's your equation. For part B, it asks us to graph this. You can put it into the calculator, but what you need to realize too is we're talking about $82,000. And so we're going to have to adjust our window here probably if you put it into your calculator. And it's okay. We just kind of have to know how to put it into our calculator and adjust the window a little bit. Because if you just put it into your normal old window, then you probably won't be able to see a picture of the graph. So to kind of show you what that would look like, and that's one of the main reasons why I wanted to show this to you. You don't necessarily need the entire coordinate plane. Just the first quadrant is probably enough because we're talking about money and it's going to grow over time. And so we're really just we don't care about like the negative money or anything like that because that wouldn't make sense in this scenario. So starting out, this one would be, let's just go ahead and put this into our calculator just to show you. And so what I would do for my graph here, this is where it crosses. So maybe I even call this like 80,000 right here. And that's where it's going to cross the x-axis. And just show that it's going to kind of grow over time. It doesn't have to be real specific. I'm not going to get real picky about something like that. And I probably wouldn't ask you like on a quiz or test to graph something like this because of the scale. We may have to do it to like solve something, and I'll show you what that means here in just a second. C wants to know what is t equals 0, t equals 2, t equals 5, and t equals 10. And this would be the real reason why I would put it into my calculator is because now I can go to my window. So 5-3 today. It's kind of like our third section row of kind of a little bit different topic. But what 5-3 does is it kind of ties the first two sections of chapter 5 together and puts them together. So in 5-1, we talked about inverses. In 5-2, we talked about exponential functions. And so our topic today are logarithm functions. And from here on out, we'll probably just call them log functions. Okay, logarithm is the actual name of them, but usually we just call them log functions. And you've seen logs back in Algebra 2 a little bit. Today we're going to just kind of introduce like what is a log, how do we use a log, what are some of the log rules, and then pretty much throughout the rest of this chapter we're going to be solving log equations and we're going to be doing some different things with those logs. But today's just kind of a introduction into some of the rules and things. So first of all, what is a log function and why do we need a log function? Yesterday, we said an exponential function would look like this. Y equals 2 to the x power. Okay. If I did the inverse of that, and this is where it ties yesterday and the day before into one, kind of, because yesterday we talked about an exponential function, and then today we're going to talk about the inverse of that exponential function. And based on what we did on Monday, we would say the equation is x equals 2 to the y. But when we write a function, we always want y to be by itself, okay? And so what we do is we rewrite that equation in a little bit different format, and that's where the log comes into play. So when I write this inverse equation of this graph, or of this function, from here on out, it would be this. Y equals log x base 2. This represents the inverse. We used that inverse terminology the other day, where if I see f inverse of x, that means this is the inverse of my original function that I had for the exponential function. Now we're going to talk about what this means and how we can get there and going back and forth, okay? But essentially all you really need to know about a log is that it's the inverse of an exponential function. And it's just a way of being able to write that equation in our y equals format, okay? So that way we now can put it into our calculator and we can do things like that. Because if I left it like this, I wouldn't be able to put it in my calculator. I wouldn't be able to graph it. I wouldn't be able to do some of those things. And so now we can do some more things and we can put it in that function form that we're used to seeing. One of probably the most common things that we're going to do, especially today, but even as we go throughout the chapter, is we're going to talk about how we can go from one to the other. And we're going to change a log equation into an exponential equation, or an exponential equation into a log equation. Okay? So here is just a generic log equation. Y equals log x base a. Okay? What we're going to do to change this to an exponential equation is we call it the log loop. And you've probably heard or seen this before. We're going to take the base of the log. We're going to raise it to the power of y. So we're going to say a raised to the y power is equal to x. And that would be my exponential function. In some cases, they're going to give us the exponential function, and we're going to have to go backwards and rewrite it as a log function. I'm going to give you a lot of different examples of that today. And then we're going to do some rules that go along with that as well. Okay? So you've got to know the log rule and how it works, and the log loop and how it works. Some of these we're going to be able to do in our calculator. And so I'm going to show you some different scenarios here. For instance, if I said, let's just go to another page here. you're going to have some problems like this today, where we're going to try to figure out what the base of the log is going to be. And some of these we can put into our calculator. Like this one here, I can put this into the calculator because the log 100 base 10 is also the same as this. If there is no base here, then my base is assumed to be 10, okay? And that will always be true for LOG. For any common log, then it's assumed to be base 10. It's kind of like if I put an X and I don't put any numbers in front of it, I always know there's a 1 in front of that X, right? Same thing here. If I put a log and it doesn't have a base down here, a base will always be 10. If I want some other base to be there, then I got to put that base there, okay? So we just got to know that these two things are essentially the same thing. And so for this one here, we could put it into our calculator, okay? So if you have your calculator, let's get it out, and you could just type in the log of 100. And you should just get 2, okay? Now the reason why this is 2 is because if I use my log loop here, 10 squared equals 100. Okay. 10 raised to the second power gets me to 100. Okay, that's why my answer is 2. And so sometimes we can just put it into our calculator. Now, if I gave you one like this, log 9 base 3. This one, eventually we'll talk about how we could put this into our calculator, because sometimes we'll get answers that are not nice whole numbers. I'm going to give you some that are nice whole numbers right here. But if I just said, what is this expression equal to? We're going to rewrite this, and we're going to say 3 to some power is equal to 9. So when I rewrite this, I could say 3 to what power gives me 9. And that would also be 2. So 2 is what goes here because my exponent is 2. And so even when the base is not 3, this one's a little bit more difficult to put into the calculator. I know that some of your calculators have log base buttons, but not all do, so I probably won't talk about that a lot. If you don't have a log base button, I'll show you other ways that you can do some things. If you do have it, then obviously I can't stop you from using it, but not all calculators will have that log base button. Some other ones that kind of go along with this. If I said log 5 base 5. 5 to what power gets me to 5? Just be 1. So if these two numbers are the same, then my answer will always be 1. 5 to the first gets me back to 5. If I gave you one like this, okay, and they're asking us, what is this equal to? I always like to kind of draw a box in here. They're not going to do this part right here. They're just going to say log 1 base 6, okay? And they're going to ask you to evaluate that. But what I like to do on something like this, just so we can kind of understand what's happening, 6 to what power gives me 1? We're just using that exponential log loop rule over and over again. 6 raised to this power gives me back to 1. So what exponent always gives me an answer of 1? 0. Okay. So my answer here would just be 0. So I like to put that box there because we're just trying to figure out what goes in that box. What is that expression equal to? So if I see a 1 in this spot right here next to the log, then I don't care what the base is. Base could be 1,000,000, right? And my answer will always be 0, as long as there's a 1 next to the log. Okay, we could see some that are a little bit more difficult. Something like this. And eventually I'll show you how you can use your calculator to do this. But just kind of understanding where that number comes from and why we get where we're going to get. 25 to what power gives me 5? And this is kind of a tricky one, and it kind of goes back to yesterday. We haven't really talked about our exponential rules much over the course of this semester. It kind of goes back, and it's one of those things that we just don't spend a lot of time on in college algebra because we just kind of assume, well, we've done exponential rules before. But this is one of those exponential rules we haven't talked about for a while. Kind of like the negative exponent yesterday and some of the things that we saw yesterday. What's the relationship between 25 and 5? Yep. If I square 5, I get 25, or if I take the square root of 25, I get back to 5. And when I write the square root of 25, then when I write that as a exponent, then I can write it as what we call a rational exponent. The exponent here is assumed to be 1. Whenever I have a square root, my root is always assumed to be 2, so I can write it as 1 over 2 power. So 25 to the 1/2 is the same as the square root of 25. Okay, it's one of those exponent rules we just haven't seen for a while. And so what I could do here is I could put 1/2 in as my exponent. And so 25 log 5 base 25 is equal to 1/2. Okay. And we probably won't see that one a ton, but it is one we could see. One more I'm going to put up here. This is another one that kind of goes back to your exponential rules. 10 to what power gives me 0.01. Okay. Well, up here, when I had base 10, I could move it 2 places. Basically, it tells me how many zeros I have when I have base 10. If I had log of 1,000, it would be 3. If I had 10,000, it would be 4. It basically just tells me how many zeros I have there. But when I have 0.01, and I wanted to figure out what this exponent would really be, okay, then what we would do, if I do 10 to the negative 1 power, based on what we talked about yesterday, that would be 1 over 10, which is 0.01, or which is 0.1. If I do 10 to the negative 2, then that would be 1 over 100. And that is the same as 0.01. Okay. And so 10 to the negative 2 gives me 1/100th, which is the decimal that I have right here. And so my exponent here would be negative 2 to get to that 0.01. Just knowing that 0.01 is the same as 1/100th. That's the decimal that we're representing. Okay, so those are just some different kind of rules and just kind of showing you how and some things to remember. We're going to kind of see some of those pop up from time to time throughout some of the things that we do, both on our lesson and on your assignment today. I'm going to give you some log rules, and these kind of go back to some of the things that we just talked about, but I'm going to kind of put them in generic form. First of all, the log loop. Okay, and this is probably the most important thing that we do today. And I already put this up here earlier, but I'm going to put it up here again because it's so important. Okay, y equals log x base a. And when I go to the exponential side, we're going to do a raised to the y equals x. Okay. And I'm I'm going to give you some examples here in just a second where I'm going to give you the exponential and we're going to go backwards. We're going to go the other way with it, okay? And just show you how we can go from one to the other. So if I said log 16 base 2 equals x, all I'm going to ask you to do here is rewrite this in log form. So now we're going the other direction with it. So when I write this in log form, I always like to write the log first. The base of, I wrote it in the wrong spot. That's my fault. I meant to write the exponential form down here. Let me write it on the other side here. Or let's write it in a different form. That's my fault. 2 to the x equals 16 is what I meant to write. And when I rewrite this in log form, just so everything's kind of aligned here, we're going to write the log base 2. The base of the exponent is the base of the log, okay? The exponent, if I do my log loop, is x. So that's going to be the number that comes over here. And then 16 comes right here. So we would just say 2 raised to the x equals 16. And we're just doing that loop again. Okay, we could see it with an e, and I'm going to show you another thing with e here in just a second. But if I just gave you something like that, I always like to write log first. The base of the exponent is the base of the log, okay, the two bases. The exponent is t is equal to 70, and that would be my log expression. Okay, let's do one more, and this time I'm going to give you the log. Sometimes we have numbers, sometimes we don't. This one has all variables in it. And so we're just going to rewrite this as an exponential equation. Okay, so I'm giving you one, you have to come up with the other. In this case, my log loop says a raised to the m power equals q. We're just rewriting it, not really solving it. There isn't anything to solve because we don't know the value of those variables. Okay, so I'm going to put a star by this because that right there is something that we got to know. We got to know how to use it, and we got to know how to go both directions with it. Okay, and those are some kind of examples that kind of show you how to go back and forth with numbers or without numbers. Okay, and a couple other quick log rules we kind of already talked about. If I have a log of 1, no matter what the base is, the log 1 base A is always equal to 0. Because what we said up above, anything raised to the 0 power is always going to give me 1. I don't care what that base is. We kind of saw it on some previous examples that we did. I put some numbers in there, but we don't really care what the number is. Okay, so that's a big one. And another big one is if these two numbers are the same, okay, and I'm just putting A in here. I don't really care what that number is. It could be 5 and 5. It could be 20 and 20, whatever it is. If those two numbers are the same, then it's always equal to 1. So if I had the log 20 base 20, then it would be equal to 1. Okay, and so those are some big ones as well. That if we see them, we should be able to look at them and immediately know if I have a 1 in this slot right here, it's always 0. If these two numbers are the same, it's always 1. Okay, Couple of things on your calculator. We can do logs on the calculator. When I have something like this especially. Remember that this is assumed to be base 10. So really what we're saying here is 10 to what power is 645,778. That's not something you're going to be able to do in your head, okay? So we're going to use our calculator. And all we have to do here, as long as it's base 10, is I just type that right into my calculator. Log of 645,778. And we're going to deal with decimals a lot throughout the rest of this chapter. We're going to round to the nearest hundredth, nearest tenth, nearest thousandth. We'll round to a lot of different place values. Here, typically I'll just go to like the nearest hundredth, probably most commonly. Okay, one we have not talked about yet is, what if I take the log of -3 in my calculator? What happens? You get an error, right? Does not exist. We cannot take the log of a negative number. Okay, cannot do it. Because what we're saying here is 10 to what power gets me to -3. There is no power, there is no exponent with base 10 that will get me to -3. So anytime you see log of a negative, that's kind of like another log rule. You should automatically know we can't do that. Now, if I give you one like this, the log of 0.462, what do we get for that one? So I kind of threw this one in there mainly because we can have a negative over here, but I can't take the log of a negative. So I want you to see the difference between that. When my number here is really small, then your answer, or when this number, here is small, then your exponent's going to be a negative. Okay? And so we can have a negative over there, but we can't take the log of a negative. So those are two completely different things. LOG is 5.81, and that's because this was base 10, right? When I do ln, it's base e. Okay, so all of those, log is what we call the common log. It's the one we most commonly use, and we'll use log more than any other. But there is one other kind of log that we're going to see. And the other log that we will use is what we call the natural log. Okay, log is always assumed to be base 10. ln is always assumed to be base e. So it's using that base e, or that number e that we talked about yesterday, and that's what the base is assumed to be. So I told you that if there is no base on log, the base is always assumed to be 10. On ln, it's always base e. So if I see ln and there's no base here, then I always assume that to be base e. Okay, another way I could do this is I could do log with it too. All three of these things are the same thing, okay? The reason we use natural logs is so I can rewrite this and not necessarily have to have the base here. And there are some times where we're going to want to use natural logs as opposed to common logs because it makes the problem a lot simpler. And we'll talk about that later in the chapter, but just trust me, ln is going to be one that we're going to want to use. We just don't use it as much. But there are times where it makes things a whole lot easier. But what happens here also is it changes some of those answers. So if I put in the same number that I did just a few minutes ago, but I use LN, you have an LN button right there in your calculator, right next to LOG. If I do the LN of 645,778, it's going to give me a little bit different decimal here. Okay, when I did, which we said yesterday is 2.7, and so on. Okay, so because the base is different, my answer is different. And we can still plug that one into the calculator, no big deal. Still with ln, if I try to do the ln of -5, what we're going to get? Same thing as we did with LOG. So we still can't take the log of a negative number. Whether it's common log or natural log, we can't take the log of a negative. So that's one thing that does not change. Okay, here's kind of one of the big ones. ln of e is the same as the ln of e base e, right? And if these two things are the same, then what's my answer going to be? 1. Okay, and we kind of talked about that just a second ago. Okay, so from here on out, the ln of e is always 1. Okay, and I'm going to put a star by that because that's really, really important. It's kind of like when we did I squared equals -1, and we said from here on out, anytime you see I squared, we always know it's -1. ln of e from here on out, anytime I see the ln of e, it's always 1. Every time, okay? And that's one thing you got to kind of keep in the back of your mind. And we're going to see that a lot later on in the chapter. And so we want to kind of keep that in mind. Okay, and then one more. If I did the ln of 1, as long as I have a 1 in this spot right here, what's it always going to equal? 0. Yep. My base here is e, but remember we said it doesn't matter what our base is. Anything raised to the 0 power always gets me back to 1, even if it's e. Okay? And so anytime I see a 1 in that spot, so that kind of goes back to the same rule we talked about just a few minutes ago. If I see a 1 in that spot, doesn't matter if it's ln or log, it's always going to be equal to 0 every time. Okay. You're going to see a couple problems today where they're going to talk about the graph of a log function. Okay. So here would be a log function. And what I want you to remember here is those two are the same thing, okay? This is the exponential form, this is the log form. On some of your calculators, if you have the log base, you can put in log base 5. Some of you do not have that log base button. Okay, so you're going to kind of have to know, how can I graph this log function without having a base in there? Here's the first thing I want you to remember. Yesterday, we graphed this function, right? And I'm just going to kind of tie all this together based on the last couple of days. This is my exponential function. But what I told you at the very beginning of the lesson today is the exponential function is the inverse of the inverse function, or vice versa. The log function is the inverse of the exponential function. So on this one here, a couple of quick points, or 0, 1, and 1, 5. And that's what we did yesterday. So if I graphed this log function here, we're going to flip the x and the y around because these are inverses. So those two ordered pairs, and I'm just picking two really quick ordered pairs to use here, 1, 0, and 5, 1. I just flip those order pairs around. And so this would be 1, 0, and 5, 1. And there would be that graph. Okay, and remember what we talked about on Monday. When we have an inverse, it's going to be flipped over that y equals x line. So here's the graph we did yesterday. This would be the graph of the log function. Okay. And those would be a couple of quick points you can do on. Now, one thing to notice that changes here. When I had the exponential function yesterday, we always said it has a horizontal asymptote, right? Always approach the x-axis as long as we didn't shift it up or down or whatever. On this one, my asymptote's going to be the y-axis. That's the graph it's going to approach and get really close to. Okay, last thing here. We call this the change of base formula. Okay. What you would need to do in your calculator here, sorry I ran out of time here, guys, is some of you can put this in just like this. You can do the log of 8 divided by the log of 5, and it's going to give you a decimal. Some of you have the log base button, and you can just use that button if you have it. Okay, and we can kind of talk about that tomorrow. If you have that, I'll show you where it's at, and you can use that. If not, you can do it the old school way and do it like that. All right, I'll put the assignment on Classroom, so it'll be in the assignment description with the video that I post. And I'll try to have it up here in the next few minutes. Well, as soon as I can get this video